Alright, so today I'm going to be explaining another important paper with the title Halting in Random Walk Kernels. This NeurIPS paper in 2015. Although it is old, it has very good insights. Random walk kernels measure graph similarity by counting matching walks in two graphs. In their most popular form of geometric random walk kernels, longer walks of length k are downweighted by a factor of lambda k to ensure convergence of corresponding geometric series. So we know from the field of link prediction that this downweighting often leads to phenomena referred to as halting. Longer walks are downweighted so much that the similarity score is completely dominated by the comparison of walks of length 1. This is naive kernel between edges and vertices. So in the past 5 videos, I talked about random walk kernels, different kinds of random walk kernel. For example, k-step random walk kernel between two graphs. It can be directly computed if weights are geometric series, resulting in the geometric version of that. So the geometric random walk kernel is one of the most popular graph kernels as it can take walks of any length into account. However, the fact that it weights walks of length k by the kth power of lambda together with this condition immediately tells us that the contribution of longer walks is significantly lowered in k. If the contribution of walks of length 2 and more to the kernel value is even completely dominated by the contribution of walks of length 1, we would speak of halting. It is as if the random walks halt after one step. So this theorem for upper bound and lower bound of this kernel between two graphs. And so what is the relationships to linear kernels on label histograms? So we clarify the relationship between K and basic linear kernels on vertex and edge label histograms. Given a pair of graphs, we introduce two linear kernels. So the vertex label histogram kernel is defined like this dot product. And similarly, the edge label histogram is a vector and dot product between them. So we've introduced the vertex edge label histogram for a pair of graphs, and their product we can have this kernel, both node and edges. So let us define a new kernel. That is, both uses the vertices kernel and the edge kernel as a linear. And finally, they did experiments on these graph classification data sets, such as this mutagen, enzymes, protein, etc. So we first compared to geometric random walk kernel to other kernels. And these are results on semi-simulated data sets. These are important data sets for graph classification. Most of them have only two classes. Because of the complexity of this task, even for simple graphs. So you see the classification accuracy on real-world data sets.